There you go. Minimize that.
Yeah.
I used the one
Yeah.
that
Yeah.
Make sure you don't fall asleep though.
Exactly.
Make sure you don't fall asleep. Hey,
All right.
Okay, so the next thing is the development length. So in development length, what it simply is saying is that if I have a concrete cross section and if I provide a pre-stressing strand, the entire length of the strand doesn't actually have the same pre-stressing force, because since the force in the strand is only able to occur because it's bonded to the concrete, what actually happens is the stress in the strand actually increases from 0 to a value of FPS within a certain length of LD, and then it has a constant value of FPS. So what it is simply saying is within the first few inches in the beam, the actual stress in the strand is less than the FPS. And what we do is we can calculate this value of LD based on the ACI formula, where LD is given as FPE, that is the effective pre-stressing stress in the strands, times the diameter of one strand divided by 3. Or approximately, if you don't know the value of FPE, you can simply use 50 times dB, where this dB is in inches and this also comes out to be in inches. So what it is simply saying is from the end of the beam until a length of LD, the stress in the strand is actually less than FPS, and it increases linearly from 0 at the end to FPS at a distance of LD. Now let's say if I increase the loading on this beam further, stress in the strand will keep on increasing. It will keep on increasing until it reaches the stress of FPS, where FPS is the stress in the strand at the nominal moment capacity of the beam. So if I want to go from FPE to FPS, I need an extra length, which is defined as LF. So LD is the length to go from 0 to FPE, and then LF is the length to go from FPE to FPS. And this LF is actually simply defined as, what is it? Is it LF? Let's see. Yep. It's FPS minus FPE times dB. So you need this length to go from 0 to FPE, and you need this extra length of LF to go from FPE to FPS. What is the consequence of this? The direct consequence of this is, if I want to check the moment capacity within this length, what is the maximum force that can actually occur in my strand? Is it AP times FPS or something less?
Less.
Within this length, my strand cannot have a force of AP times FPS, right? So if my strand cannot have a force of AP times FPS, that means my moment capacity or the value of Mn is not based on AP times FPS. So within this region, you cannot use your tension in the pre-stressing strand is not equal to AP FPS for X less than LD plus LF, where X is actually measured from this point. So now if you go back to how we calculated the moment capacity of the cross section, we assume that my tension in the pre-stressing strand is actually AP FPS, which is not the case within this range. So that will directly affect my moment, the nominal moment capacity of the beam itself. And then this also has effect on the shear capacity of the beam, which I'll go into next. So for the shear design, there are two kinds of shear failure in concrete. So if this is my, let's say, simply supported beam, and let's say if I have a uniform load on it, if I look at the crack patterns near the center of the beam, what you will see is cracks which are perpendicular. And these perpendicular cracks actually correspond to flexure cracks. If you go a little bit further towards the center, what you have is a crack which starts at as a flexure crack, but as it reaches towards the middle of the cross section, it actually changes to a shear crack. So these are actually called flexure shear cracks. So it starts as a flexure crack at a 90 degree to the surface, but as you go towards the center of the beam, it actually changes to a shear crack. If you go further towards the support, what you actually see is just a shear crack. Because what is actually happening is near the support, my moment is actually small, but my shear is actually quite large. Because my moment diagram looks something like this. So my moment actually gets smaller towards the support. But if I draw my shear diagram is actually a maximum near the supports and a small near the midspan. So near the supports, it's actually dominated by shear cracks. Between the support and the midspan, it's a combination of both the flexure crack and the shear cracks. And near the midspan, it's actually dominated by the moment. So you will only see moment cracks. So now what we need to do is we need to find out what is the shear capacity of the concrete itself. So we have a different formula for both the shear crack and the flexure shear crack. So for the flexure shear capacity, that is these cracks, the capacity, the shear capacity of the concrete is given by 0.6 square root F prime C BW times dP plus VU over MU times MCR, where this PW is the web width this dP again is the distance from the compression to the centroid of the preceding strand. This is the factored shear demand. This is the factored moment demand. And this is your cracking moment. So when I say the factored shear demand and the factored moment demand, what you are actually supposed to find out is VU is the shear at any given cross section due to the factored loads. By factored loads, it's 1.2 times the self weight plus 1.2 times the dead load plus 1.6 times the live load. Similarly, this MU is the moment caused by the factored loads. Again, the factored loads are 1.2 times self plus 1.2 times dead load plus 1.6 times the live load. And this MCR is the cracking moment. So what this equation is actually accounting for is, this is the amount of shear force that you need to start the flexure cracks, plus in order to propagate that flexure crack into a shear crack, you need this extra term. So this is accounting for the initial origination of the crack, which is a flexure crack, and then this accounts for the fact that if you want to propagate that crack into a shear crack, you need this more, you need this extra force or a shear force to create this part of the crack. And this formula is only applicable if all loads are uniform loads. So if all the loads, that means your self weight is always uniform load, your dead load and your live load. If all of them are actually uniform loads, you can actually use this formula to calculate the value of VCI. Now let's say if my dead load or my live load is not a uniform load, there is a slight variation to that formula. One more thing, actually, this dP, it is the maximum of the actual dP, that is the distance to the centroid of the preceding strand, or 0.8 times the height of the cross section. So let's just call this D actually. So if your strand is closer to the centroidal axis, your D actually becomes 0.8 times H, and if your dP is actually greater than 0.8 times H, then this D actually becomes dP. That is the distance from the top of the compression phase to the centroid of the preceding state. So again, this formula is if all the loads are uniform loads. If your loads are not uniform, then VCI is given by 0.6 F prime square root F prime C. One more thing, this is in PSI. So if this is in PSI, you have to take care of the units on the rest of the terms. So the first term still remains the same. This is BWD plus V naught plus VI over M max times MCRE. And in this case, the first term is exactly the same. V naught is the so V naught is the shear at that particular cross section due to the self weight, which is unfactored. So you will just simply use omega naught to find out this value of V naught. This VI this is the so VI is the shear at that particular cross section due to the factored loads except the self weight itself. Yeah.
Do you actually have any white chocolate?
Yeah, I do. Yeah. Should I rewrite this?
It's alright.
Oh, okay. So VI is the shear at that particular cross section due to all the loads except the self weight, because the self weight is already accounted for in this V naught. And all these are calculated based on the factored loads. So it's 1.2 times the dead load plus 1.6 times the live load. And this is simply your self weight, omega naught, without any factors. Similarly, this M max is the moment again, which is this same value. So Vi is the shear due to this factored loads except the self weight. M max is the moment due to the same load without the self weight. And this MCRE is defined as the cracking moment minus the moment due to the self weight. So this is actually MCR minus moment due to the self weight. So these two formulas are actually exactly the same. The only thing is if all the loads are uniform loads, then you can go ahead and simply use this where you have all the loads factored and you find out VU and MU. If any one of your loads are not uniform loads, then you have to actually take the self weight separately and the rest of the loads separately. Yeah.
So is that M max the same thing as M?
Yeah, actually,
No. It's
it is actually delta M, but with the factored loads, because the M max that we use in feasible domain or the limit zone, it's the unfactored loads.
Oh, okay.
But in this case, it's the factored loads except the self weight. Okay. And there is another limit which says that VCI from both of these formulas has to be greater than equal to 1.7 square root f prime c bw d. Again, this d is same as right here, maximum of dp or 0.8 times h. Yeah.
So I was wondering, like, for D, there's times where like you write the equation and you specifically say that the D is to all the pre-stressing steel, including mild reinforcement, and sometimes you'd be saying the DP is only to the pre-stressing steel.
In my notes, I have it's the centroid of the tendon actually. For this case, at least. Yeah. Even if you make that error, like instead of finding DP at the centroid of the tendon, you find it DP in the centroid of all the strands. In this case, don't worry about it. I won't take points off. Yeah. Because it's not a mistake worth like any points actually. Yeah. So, but in my notes, I have it where he says, okay, it's no, it's actually to the centroid of all the steel. Yeah, it's centroid of all the steel.
Confusing because there's like DP mixed up.
Yeah, yeah. So in this case, this DP is actually to the centroid of all the steel. Okay, so don't make that mistake. I'll take points off. Yeah. Okay.
It seems like there's some cases where like they actually want, like on one side for it to be DP only to the pre-stressing steel.
Yep. Yep.
But like, it's not really clear.
No, it is clear if you actually look into the fine prints. But since we keep on using the same name for all centroids, so in some formula, if you are just using the centroid of the pre-stressing steel, they'll still use DP. Like in shear formula, it's to the centroid of all the steel. They use the same convention, that is DP. So that's why it's actually confusing. If you actually look into the text, it will say clearly whether it's just to the centroid of the pre-stressing steel or to the centroid of all the steel. But in this case, for shear design, it's to the centroid of all the steel, this DP.
So why don't we just call it DE?
But I think on the left side,
Call this DE, yeah, call this DE.
What does it stand for?
Yeah, why not? Yeah.
but I'm pretty sure
I mean,
that
it's like in a textbook.
for up there on the top, 0.6 has that one.
It's like something that's just like so not intuitive.
No,
I'll try to read
It's
the
so
book and see
picky.
if I can find that.
I'm following the notes. I'm not following the book. I'm following the notes.
Right.
Yeah. Yeah.
So you rate the flexure shear capacity, but it's
Say it again.
labeled flexure shear capacity,
Yeah.
but it's done in
It depends on the demand, because what you are trying to actually do is saying that, so MCR is the moment which corresponds to the first flexure crack, right? So if I apply a load which produces a moment of MCR, you'll actually get this flexure crack. So what you are actually trying to do is by multiplying it by this ratio, you are trying to find out the corresponding shear which will actually create that crack. Make sense? So what you have is a moment capacity or the moment which will create that first flexure crack, and you want to convert it to a shear which will create the first flexure crack. So what you do is you just multiply it by this factor of Vu over Mu, and it actually gives you what shear will actually produce that flexure crack. Doesn't make sense. Or doesn't make sense? Find out the shear capacity of the concrete. Does it make sense or not? Because so what this second term is actually the shear required to cause this first crack, which is the flexure crack. But there is no direct way to actually to relate the flexure crack with the shear capacity. So what you do is you take the flexure moment, the cracking moment, divided by the corresponding moment which is applied due to all the loads, which is the self-weight and the dead load and the live load, and you multiply it by the corresponding shear. So what this term is approximating is the shear required to cause flexure crack. This is trying to approximate the shear which will actually produce that first part of the crack, which is actually a flexure crack. And then the next part, which is actually a shear crack, is taken into account by this the first term actually. Make sense? And I think they are trying to relate it to the demand rather than the demand, because this is your capacity, right? Your MCR is the capacity before which it actually cracks. And this Mu and this Vu are directly related to each other by the fact that the value of Vu and Mu will depend on what kind of loads you have. So it's just simply trying to convert this capacity, which is currently a flexure capacity, into a corresponding shear capacity. Yeah.
If we're only looking at the supports, could we not even look at that part of the equation? Because, you know what I'm saying?
Say it again.
If we're only looking at the supports, do we ignore like the right side of the equation since there are no flexure cracks?
Actually, yeah, you can do that if you are just looking at the support, and that's what I will show you in 5 minutes. Okay? Yeah.
So back from what I was saying, are you saying, if we do have mild steel, whenever there's any D in any equation, it's always do it in the centroid of all the
I won't say any equation, at least for shear, it's the centroid of all the steel. Yeah. Okay. Where else do you have D?
No, I'm just saying like anywhere in the equation.
Yeah. Oh, yeah. In this equation, anywhere if you have a D, it's the centroid of all the steel. Yeah.
That 1.7 F prime C, is that a limiting at the very bottom?
Oh, yeah.
Is that a limit on the equation, or is that a design?
It's a limit on the equation saying that if you get a value of VCI which is less than this, you actually use this. So this is like the minimum that you should get from either of these two equations. So let's say if this gives you 100 kips, and either of these two equations, depending on what kind of loads you have, if this gives you 90 kips, you actually use 100. Okay? It's the web width. So if you have a flange section, BW is the web width, not the flange. Okay? So this actually gives you the VCI, which is the flexure shear capacity. Now we need to find out what is the capacity for just the shear cracks. So for the web shear crack, you have a formula VCW, and this is 3.5 square root f prime c plus 0.3 fpc bwd plus bp. Again, rule of the thumb is as soon as you see a square root of f prime c, it's always in psi. Okay, so this is in psi. FBC is the compressive stress at the centroid of the cross section or the centroid of the section due to the pre-stressing force. So if I have a cross section, this is my centroidal axis. If I have a pre-stressing force of F acting at a distance of E naught, what is the stress at the centroid due to this pre-stressing force and E naught? Sorry? My over I, but y becomes 0. It's simply F over AC, right? So at the centroid of the strand, my FPC is simply whatever the pre-stressing force is at that location divided by the area of the cross section. How do you get this? What I can do is I can use the method of superposition. This thing is exactly the same as F acting at the centroid plus a negative moment of F E naught. This gives me a stress at the centroid of F over AC, and since this is a pure moment, it gives me a 0 stress at the centroid. So the overall stress due to the pre-stressing force F and the eccentricity E naught is always F over AC. So this FPC is simply F over AC. Again, this BW is the web width. This D is the maximum of DE, comma 0.8 times H. And then this VP is compo F. So if your tendon is actually draped, if it's not a straight tendon, so if my tendon has any angle to it, so technically my pre-stressing force is acting along the tendon itself. So if my tendon is at a certain angle, I actually have some amount of vertical component to that force F. So if this angle is theta and this pre-stressing force is F, then the vertical component I have is F times sine of theta, and that is actually my VP. So if my tendon is at a certain angle, what actually is happening is that vertical component of the tendon is going to resist some of the shear loads. So I account for that vertical component in this term VP. If you have a straight tendon, this becomes 0. If you have an angle to your tendon, then you'll have a non-zero F sine of theta. Okay. Now the thing we actually talked about the development length, that actually comes into play in this term and in this term. Because if I go near the supports, my actual F in my strand is not FPE times AP, because it has to increase from 0 to FPE over a distance of LD. So within that distance, your FPC is actually not simply F over AC, it's something else. It's less than F over AC, because the actual force within that length is less than FPE times AP. And the same thing is for VP. Within that length, this F is less than FPE times AP. So you have to account for the development length within that length of LD. So that's where the development length comes into play in the shear design. Okay. So now this, either this or this gives me the flexure shear capacity. This equation gives me the web shear capacity. the actual capacity of the concrete, where should I write it? It is this. So these two formula VCI, either based on this one or this one, and VCW, they are only accounting for each type of shear failure. Now what we need to do is find out the actual VC, which is the shear capacity of the concrete itself. It is given as the minimum of VCI and VCW. And what actually happens is if you draw both of them, so this is, let's say, distance x. So at x equal to 0 is your first support, and this is x equal to L is the second support. What you'll see is VCI will decrease, doesn't go to 0. VCI will actually decrease as you go away from the support, and VCW remains more or less constant. It's not exactly constant, but it remains more or less constant. So now what it's simply saying is near the supports, so this is my VCI, this one is VCW. So it is saying that near the supports, it's the web shear crack which actually governs my shear capacity. And as I go away from the support, it's the flexure shear crack which actually governs my capacity. So my actual VC, which is the shear capacity of the concrete itself, is the minimum of these two. And it automatically accounts for the fact that near the supports, it's the web shear failure, and near the away from the support, it will be actually a flexure shear failure. So this gives you the actual shear capacity of the concrete throughout the length, throughout the span. You know what is your demand, the shear demand throughout the length, which is based on factored loads. So it's 1.2 times self weight plus dead load plus 1.6 times the live load. So this is my demand. This is the capacity of the shear capacity of the concrete itself. What is my total shear capacity if I also have stirrups? My total capacity is the capacity of the concrete plus the shear capacity of the steel. This is my total nominal capacity multiplied by phi. This has to be greater than or equal to my shear demand, which is VU. For shear design, this phi is always 0.75. What is the reason this phi is actually less than the phi that we generally use in moment the moment check? Yeah. So the thing is, if a beam fails in shear, it is going to be a brittle failure. It will happen suddenly, which you don't want. So what you do is you reduce the capacity of the beam by a greater amount to make sure that that brittle failure actually doesn't happen. In case of a flexure failure, it's actually a ductile failure. So even before the beam actually fails, you will see a lot of deformation in the beam. So that's why we have a smaller strength reduction factor for the shear capacity. So now what we have is, we know the value of VU, we know the value of VC based on VCI and VCW. I can calculate what is the shear capacity which needs to be provided by the shear stirrups, VS. Then VS, again VS has a formula. VS is given by AV FYT times D over S, where AV is the total area of one shear stirrup. So if you provide a shear stirrup which is a U shape, and let's say if I use a number 4 bar, So since I have 2 legs of shear stirrups, my AV is actually 2 times 0.2, where 0.2 is the area of one number 4 bar. If you provide 3 legs, it actually becomes 3 times 0.2. So it's not just the area of one bar that you are going to provide. It depends on how many legs of stirrups you are actually providing at that cross section. So that total area is your AV. FYT is the yield stress of stirrups. Again, we use 60 KSI. D again is the depth of the it's DE or 0.8 times H, and S is the spacing. ST. S is the spacing between the stirrups. So based on this formula, I can find out the value of Vs as Vu over phi minus Vc. So I know how much Vs I need. Now you have one equation and you have 2 unknowns, AV and S, but you only have one equation. So what we do is you either pick the value of AV to begin with. So you say, oh, I'll try to provide 2 legs of number 3 stirrups. So you'll fix the value of AV and find out the value of S. Or you can say that, okay, I want to provide the spacing of 12 inches. So you'll pick a value of S and find out the corresponding AV which will satisfy this equation. Okay. Generally people actually pick this and find out the value of spacing. Then there are some other limitations on all these. So there is a limitation on the spacing which says S has to be less than or equal to minimum of D over 2 or 12 inches. And what else? And there is a formula for AV min also. This is 0.75 square root F prime C B W S over F Y T. This has to be greater than B W S over F Y T. And and if Vs is greater than 4 square root F prime C BWD, then S has to be less than or equal to no, hold on a second. That's for this is for reinforced concrete. Sorry, this is 0.75 T, and this is 24 inches.
Is it G or H?
What?
Is it G or H?
Oh, it's H. Thank you. So that's the total height of the cross section. And in case your Vs comes out to be more than 4 times square root F prime C BWD, then the maximum spacing actually is minimum of 0.375 H and 12 inches. So you calculate the value of Vs from this formula, and if this Vs is greater than this 4 square root F prime C BWD, then this is the limit on the maximum spacing. If your Vs from this formula is less than 4 square root F prime C BWDP, then you have a different limit on the spacing. So if you have more shear that has to be carried by the stirrups, you need to provide a smaller spacing compared to if you have a smaller shear which needs to be carried by the stirrups. So what you do is find out the Vs. Based on this Vs, you check whether it's greater than this value or not. If it's greater than this, this becomes your maximum spacing. If it's less than 4 square root FMC BWD, then this becomes your maximum spacing. Once you have the maximum spacing, you can actually pick the value of AV from this formula. Once you have the value of AV, you make sure that AV is greater than AV min, which again is dependent on the spacing itself. So what you do is get Vs, find out what is the maximum S that you can have to provide depending on this value. Once you have the maximum spacing, plug the value of maximum spacing here, find out the AV based on this formula. Once you have the AV, also plug the value of S in this formula and pick the AV which is larger between these two. If this formula gives you a larger AV, pick this. If this gives you a larger AV, pick this. Okay? So it's just a lot of checks that you have to do in case of a shear design. You have a limitation of AV min, you have a limitation on S and other things. There is one more condition which says that if VU is less than 0.5 times phi times VC. So technically what will happen is, if you just look at this equation, you'll say that, okay, if my phi VC is greater than VU, I don't need to provide any VS, right? But what ACI says is, if your phi times VC is greater than VU, that is, if VS from this formula comes out to be negative, still you go ahead and provide the minimum required. So if Vs comes out to be negative from this formula, you still go ahead and provide the minimum required stirrups, even though based on the formula you don't need anything. Only and only if your VU is less than 0.5 times VC. So let's say this is my VC, right? And this, let's say, is let's say this is phi times, this is VC, this is phi times VC. If this is my VU, even though technically my VU is less than phi times VC, you cannot still say that, okay, I don't need to provide any stirrups. What ACI says is, if your VU falls below, and this is your, so what ACI is saying is, within this range up till this point, since your VU is greater than phi times VC, you have to provide some stirrups. Within this range, even though you don't need any stirrups based on this formula, you still go ahead and provide the minimum required. You only don't provide any stirrups if your VU is less than 0.5 times phi times VC. So only beyond this point you can say that, okay, I don't need to provide any stirrups, which is 0.5 times phi times VC. Above that, you have to provide some amount of stirrups, which can be either the minimum or which can be based on the formula for VS. Okay. Actually, there is another value, another formula for AV min. Just go and look into your notes. I don't want to confuse anyone. So you have one formula for AV min, you have another similar term for AV min. So you just have a lot of equations that you just simply need to check. The whole idea is first find out VCI, which is the flexure shear capacity. You find out VCW, which is the web shear capacity, and the actual shear capacity of the concrete is the minimum of the two. So it becomes this. This actually becomes your VC. Once you have the VC, you can calculate your VS. And depending on what the value of VS is, you can actually calculate your spacing and the value of AV. Where AV could either be the minimum value or more than the minimum if required. Yeah.
kind of question would be asking
Like for shear design?
Yeah.
So again, just like I think, at least what I think is like just like the limit zone, you might be asked, okay, what is the shear requirement at this cross section? And you're videotaping me. So what is the shear requirement at that particular cross section? Yeah. So you don't have to do it for the entire beam again.
So can't really space it like one section.
So again, so the spacing that you provide at a particular cross section, right? It's not just valid for that particular cross section. It's valid for a few inches on both sides. So let's say if you look at the solution for the assignment, right? What I had was the value of x, that's the distance from the support. Then I have s calculated, and s calculated was like 18 inches, 16 inches, 17 inches, 12 inches, 10 inches, right? So these are the required values based on that particular cross section. So what generally we do is for the certain amount of length, we'll actually provide which will satisfy all of them. So within this length, the minimum is 16, I'll provide 15. So within this length, I will provide 15. Then beyond this, it's 12 and 10. So within this, I'll provide like let's say 9 inches or 10 inches. Okay. So once you have the calculated required, you break it into sections. And in each section, you provide one spacing which will satisfy the entire section. And don't make like 10 or 20 sections. Like in a real case, if you're designing you're doing a shear design, right? Don't pick several sets of spacing. Make it like maybe 2 or maybe 3 sets of spacing. That's it. So one near the midspan and one near the supports. Okay. Yeah.
Would there ever be a case that AV min doesn't pass the greater that 50 BS EWS FYT?
No. What it is saying is you calculate AV min based on this formula. You calculate AV min based on this formula, and you pick the larger one.
Oh, okay.
Yeah. Any other questions? Okay, I have 2 more topics, I guess. Do you want me to cover deflections? Yeah.
That was easy homework, right?
That's the one after this, number 6. That's the one that, oh wait.
No, I remember the
Maybe I
Oh, that was not the easy homework.
Okay, one quick question. How many of you actually studied before you came to the review session? Yeah, okay, nice.
Oh, yeah, 7.
I didn't get to share this.
Well, I would.
How much time?
Let's say this thing is
One of the last things we learned was better management. That's all.
Oh, yeah, just kidding. You don't have to. Yeah, that's
Okay, so for the deflection calculation, so if you have a simply supported beam, of length L, and if I have a uniform load acting on it, let's say omega naught, in this case, my deflection at the midspan, I call it delta M, it's actually given by 5/48. The curvature at the midspan times L square, right? P is unit, yeah. So if I have a simply supported beam which has a uniform load acting throughout the span, the deflection at the midspan, which in this case is the maximum deflection, is given by 5/48. Curvature at the midspan, which is phi m L square. How do we define curvature? Curvature is defined as nothing but the moment divided by EI. So my curvature at the midspan simply becomes my moment at the midspan divided by EI. Similarly, if I have the same beam, but if I have a point load on it, In that case, my delta M is given by, I think it's 1 over 12. Is it 1 over 12 or 1 over 8? 1 over 12? It's either 1 over 12 or 1 over 8. Just check your notes. No, I think it's 1 over 12. Oh, for the constant mode, yeah. Again, L square. Okay, so for this case, for a simply supported case, for a uniform load, this is given as omega naught L square of 8. That's the moment at the midspan. For this case, when you have a point load acting on it, let's say the force is P, the deflection is given as a factor which in this case is 1 over 12 times the curvature at the midspan, L square. And in this case, the moment at the midspan is PL over 4. And your phi m is still the moment at the midspan over EI. And the third case that we might have, which generally occurs, is a case where you have a constant moment throughout the span. In this case, the deflection at the midspan is given as 1 over 8, again phi m L square. In this case, phi m is simply m external divided by EI. This is m external, m external. So why we actually write it in this form is to just see that in each of these three cases, my deflection at the midspan is directly proportional to my curvature at the midspan, right? And the constant is simply L square, which is the span times square, and the only thing which is changing is this factor. Depending on what kind of loads I have a different factor in front of each one of them. So, or I can say that delta M is actually equal to K, that factor K, which is either 5 over 48 or 1 over 12 or 1 over 8 times phi at the midspan times L square. So depending on what loads you have, you just simply plug in the relevant value of K and you'll find out the deflection for that particular load. So this is for external loads. I'll keep this right here. Delta equal to K phi L square midspan. So these are the formulas for the external loads. Now let's say I have a beam which has a constant eccentricity tendon on it. So due to the tendon which has a constant eccentricity of, let's say, E naught, what is the moment profile, moment diagram for this case? What is the moment due to a pre-stressing strand which with a certain eccentricity? It's minus F E naught, right? So if my E naught is constant, that means my F E naught is constant. That means this case is actually very similar to this case. The only difference is in this case I was applying the external loads or applying the external moment. Here that external moment is caused due to the pre-stressing force and the eccentricity E naught. But still, technically these two are exactly the same cases, this and the last one, because they both create constant moment throughout the span. So for this case, my delta is simply 1 over 8. What is the moment? In this case is minus F times E naught divided by EI. This actually gives me the curvature at the midspan times L square. Now next case for the pre-stressing strand is, what is it? So this is the centroidal axis. Let's say I have a drape tendon. So it's a straight line, it has a kink, straight line goes back to 0. So we also have learned that what is the equivalent load corresponding to this drape tendon? It's a point load at the location of the kink, right? So this is similar to a case which has a point load acting at the midspan. let's call this P equivalent. In this case, my delta actually becomes 1/8. What is the moment at the midspan? It's F times this E naught, right? So minus F times E naught at the midspan over EI L square. So you don't even have to calculate this P equivalent. You just need to know that, okay, these two are equivalent to each other. And then what you are simply doing is you are simply using this factor. So this factor times whatever is the curvature, whatever is the curvature at the midspan. Curvature at the midspan is simply moment at the midspan divided by EI. Moment is simply F times E naught at the midspan. And I can directly go ahead and use this formula. The next case is when we have a parabolic tendon. Yeah. Oh, because if your E naught is positive, that means your E naught is below the centroidal axis. The moment due to the precessing strand is actually a negative moment. So that's why you always add a minus sign in front of the F E naught. And so if E naught is negative, that means the tendon is above the centroidal axis. Minus F E naught directly gives you a positive value. Right? So in case of parabolic tendon, the equivalent load for a parabolic tendon is a distributed load, which is same as this. So I can directly go ahead and let's say at the midspan again it's E naught M. So in this case my delta is simply given as 5/48 again F E naught M over EI L square. So for these three simple cases, what I am simply trying to do is for each case I am trying to relate it to a equivalent case where you actually have an external load. Yeah.
If you break that apart, say like you drew the draped tendon with the straight line, yeah, you drew it back to the centroid, but we've seen a lot of them that are down.
Yeah, okay, I'll actually do that. I'll do one of those.
You see superposition.
Yep, so you just simply use superposition. So these are the three cases for the tendon profiles. So if you have constant eccentricity, you use this formula. If you have draped tendons and they both go back to 0 at the ends, then you use this. If you have a parabolic tendon, 0 at the ends, you use this. So as the question is, what if I have a strand which is parabolic but doesn't go back to 0? What do I do it in this case? So what in this case I can do is, so let's say this one is E1 at the ends and this is E2 at the midspan. So what I can do is I can break it into two parts. The first part is a constant E1 throughout, right? Plus a parabolic case where it goes back to 0, where at the midspan it's actually E2 minus E1. Right? So this is the sum of a constant E naught and a parabolic E naught with zeros at both the ends. The deflection due to this is 1/8 minus F E1 over EI L square plus deflection due to this, which is 5/48 minus F. What is the eccentricity at the midspan? For this case, it's E2 minus E1. So E2 minus E1 over EI L square. And this gives, the sum of these two gives me the deflection for the case where I don't have 0 eccentricity at the ends. So you can always go ahead and use superposition principle if you have tendons which are not these three cases. Okay. So I think for the deflection calculation in the lecture, I derived the equation for a case where the tendon profile was something like this. So even in this case, you are using the, actually in this case you are not using the method of superposition. In this case you are using the moment area method. Okay. So now what we have is a formula for deflection due to the external loads, depending on what kind of loads I have. And I have a formula for the deflection due to the preceding forces, depending on what kind of profile I have. So now comes the total deflection. Oh, not the initial. So first one is the instantaneous deflection. So what I have is a beam. I have some tendon profile on it. I have some loads acting on it, which can be self-weight, dead load, and live load. And I want to find out what is the deflection right after I apply all those loads. So I want to find out what will be the deflection right after all the loads are applied together. So in this case, again, I can use the superposition. So my total deflection instantaneous is the deflection due to the preceding strand plus the instantaneous deflection due to my self weight plus the instantaneous deflection due to dead load plus the instantaneous deflection due to live load. Now the question is whether I use Fi or I use the effective preceding force when calculating this deflection due to the preceding strand. That depends on the problem statement. So the problem statement will tell you whether to find out the instantaneous deflection right after stress transfer. In that case, your preceding force is Fi. If it says find out the instantaneous deflection at service condition or when the preceding force is effective preceding force, this will be based on F, that is eta times Fi. So then in that case, the problem statement will tell you whether to use Fi or F for delta P. And then depending on what kind of strand profile you have, you will use either of these three factors to actually find out your deflection. Okay, so this is the instantaneous deflection. Next is the long-term deflection. Yep. Service. So before I actually go into the formula, so what I want to discuss about is creep. So creep is simply the increase in deflection at a constant load over time. So what it is simply means is if I have any specimen, if I apply a load on it and if I keep the load constant over a length of time, what you will see is even though the load is constant, the deflection will actually increase. So that phenomenon is actually called creep. So if I draw my time and let's say the strain value, so as soon as you apply the load, you get some instantaneous strains. So let's say this is the time of load application. So I get epsilon Ci, which is just due to the load applied. And even if I keep the load to be constant, what you'll see is this strain will actually keep on increasing until it plateaus off after a very long time. And this increase is the increase due to your creep, epsilon Cr. Actually, this is epsilon Cru because this is the ultimate, that's the maximum. And there is a factor called the creep coefficient Cu, which is epsilon Cru. That's the increase due to creep divided by the initial strain or the instantaneous strain. So what is the total strain? Total strain is the initial strain plus the strain due to creep. So the total strain actually becomes the initial strain times 1 plus Cu. Because this Cu is the ratio of the increase divided by the initial. It's not the ratio of total by the initial. So this is Cu times epsilon I. This is epsilon I. So the total actually becomes epsilon I times 1 plus Cu. So what it simply means is, if initially you had a strain of epsilon I, over a very long time you'll have a strain which is epsilon I times 1 plus Cu. So I can actually go ahead and use this to find out my long-term deflection. And another thing to actually see is my phi, that's my curvature. It's nothing but my strain at the top minus strain at the bottom divided by the height. So my phi is actually, this is epsilon top, this epsilon bottom, and this angle is actually my curvature. So if over time both of these values increase by the same factor of 1 plus Cu, that means over time my phi will also increase by the same factor of 1 plus Cu, because it's just a linear relationship, right? So in case of a long-term deflection, and other thing is, the creep will only occur for loads which are applied on the system for a very long time. So creep won't occur for a live load, because live load by definition is a load which can be there or cannot be there, right? So let's start with the dead load. So this is the deflection, the instantaneous deflection due to the dead load. So what is my long-term deflection just to a dead load? It's simply this times 1 plus Cu. Why? Because self weight is a sustained load. It's always applied on the specimen. The same thing with a dead load. If I have an instantaneous deflection of delta di, I'll just multiply it by 1 plus Cu, and this gives me the long-term deflection due to the dead load. Plus the third term is delta instantaneous due to the live load. Again, as I said, I don't multiply it by the factor 1 plus Cu, because live load is not a sustained load. So it's not applied over a very long time. So I have accounted for everything except for the deflection due to the pre-stressing strand. The one problem with pre-stressing strand is the force in the pre-stressing strand itself changes over time. So instead of just the force being constant and the strain changing over time, for a pre-stressing strand, both the force and the strain are changing over time due to stress loss in the strand and creep in the concrete. So in the way to account for that is, you say my initial deflection is due to the effective pre-stressing force, which is F. I think during the lecture he said this as delta Pi. And to account for the creep, you actually take the average of the initial deflection due to the initial pre-stressing force and the effective pre-stressing force. So you say delta Pe plus delta Pi divided by 2 times Cu. So this accounts for the instantaneous deflection, kind of, and this accounts for the additional deflection due to creep. And this is just an approximate value, because both the concrete is creeping over time, plus your pre-stressing force is also decreasing over time. Yeah.
So that term, the last term, is increased deflection upwards.
Where?
The last term.
This one? This?
Yeah. So because we can get more deflection upwards.
Yeah. So it will keep on. So these two terms will be negative depending on what your strand profile is. So if your strand is below the centroidal axis, they both are actually negative values.
So your creep actually helps to increase the upwards deflection.
Yeah. So it is possible that so if you have the correct amount of pre-stressing force and the loads, it is possible that over the long term your beam might not deflect that much, or it might actually deflect upwards. So initially it might actually deflect downwards, but over time it might actually go up because of the creep effect. Yeah, because these two terms will be negative if your E naught is positive. I think during the lecture at least I have an email from Professor Singh which he said that he might have mentioned it wrong. This is actually due to the effective preceding force, not the initial effective. So don't use delta pi here. This is delta PE, this is the average of the two times CU. So this accounts for the instantaneous and this accounts for the creep effect over time. One more thing. Yeah. When calculating all these deflections, OI, DI, PE, and PI, you always use ECI, which is based on F prime CI of the concrete. That is the initial strength of the concrete right after stress transfer. But in case of delta Li, you use EC, which is based on F prime C. Okay. So because EC is used in finding out this phi, right? Right here. EI, even for the loads you have moment at the midspan divided by EI. So for all the other terms you will use the initial ECI, which is based on F prime CI, but for the live load you always use F prime C. For the dead, let's see. Actually, yeah, dead will for dead also you'll use the EC. Say it again.
Does it depend when you
Yeah, because it is assumed that both the dead and the live load are applied at service condition, right? And you also assume that at service condition your concrete has already gained all the strength it has to gain. So for DI and LI you use EC, which is based on F prime C. And for OI, delta PE and delta PI you use F prime CI, because these loads are applied right from the very beginning. Okay. Say it again. You'll use the F prime C for the dead load and the live load. But for the other three cases, which is delta PE, delta PI, and the delta OI, you use the F prime CI to calculate your E. What else? What else? What else? Is there anything else in this? I don't think so. No, Christina is holding an office. I don't know. Oh, you guys are sleepy or what?
Keep going all the way.
Yeah.
Can I take
No, if you want to take a 5-minute break, I don't have a problem.
Alright, no, just go.
Okay. Next thing is, so
I don't know,
next thing I have is continuous beams and composite section, composite beams.
So delta, delta not is the only thing with ECI.